I thought this would be a really good project for our exploration of architecturally exposed structural steel. This is the Renzo Piano's addition to the Chicago Art Institute. Um, it's in Chicago, so the climate's really harsh. This is exposed structural steel. And I think it's an example of we're going to do this in a parametric form, but it's a really great way to look at how critical it is to think about the size of the elements. And, primarily here, these very slender columns supporting these what look like really large loads up on top. So I've kind of reduced this down to a simpler project. I've taken some of the best images I could and kind of like deciphered down the grid system that this might be built on, get some basic ideas for what the dimensions of the components are, and then kind of put it together in a project that we can build so we can get a good idea of, what kind of issues we might face if we were developing something like this. So let me close this down and show you what it looks like. Kind of, actually, I'll go right to this view. This is kind of where we'll go with the model. I really kind of greatly simplified it. I've got two grid systems. That'll be the first thing we start on. And then we're going to build these parametric components. For instance, this beam is parametric. We can control the depth of it and the width of it. If I was to exaggerate it, let's say I want to make it slender. I'm going to change the depth of it down to, let's say, 3 feet and maybe only 8 inches wide. And apply that, and now we have much more slender components. But those may not meet structural goals. So let me just reset these back again. So that's going to be issues that we're going to need to have in discussions with our structural engineer. And we have the same kind of flexibility we're going to develop into our parametric component for the vertical column. So the vertical column, if we go to edit type, I've created, as we go through the experiment, these pass-through parameters. For instance, the column radius is 10 inches. We can control the taper depth. So if I was to, let's say, need to make these columns like twice as large in diameter, you can see how they then become kind of massive and relatively gaudy looking. And so this is a critical element for us to have discussions with as far as what we need to do to accomplish our goals visually, and what between that and the structural engineer, what he needs to do to make sure that the components can perform as needed to support the loads. So we're going to put that together. We're going to, if we were to zoom out, we're going to go ahead and flex those parametric values to look at how our structure looks different by changing the different size of the componentry. And that's going to be based on kind of what we do prior to that, and that's kind of our analysis of the structure. So we're going to put a tributary load over a column area that we can also look at the beam analysis. So we can put that load across the beam and then use a web-based tool to determine how deep it needs to be, at least a basic wide flange section would be. So we get an idea of the approximations of it. And then we're also going to use another web calculator to figure out the strength that we need for the column. So I hope it's intellectually engaging and helps you to, feel more empowered to have these kind of structural discussions, especially when the look of the structure is really critical, as it is in a project like this. So next we'll get started with just laying out these grids. These grids are based on some of the research I did of the building and help us to set the kind of scale and massing of the building we're going to make.